Okay, good morning, everyone. Just a quick announcement before we start the class. You have an exam, as you know, on Friday at 5. Yeah, so that's your third exam, and you still have the final, of course. The coming up exam on Friday is going to be exactly the same format as the one you just did. So it's going to be online, on Moodle, and you would be, proctored through your cell phone cameras, and you will be able to run your code through the, the editor, the plugin editor on it. Okay, so basically pretty much the same experience as last time. Right now, what is the material relevant for the exam? So everything, up to and including complexity. So the stuff we're going to talk about today on Friday are not included, right? So anything up to the last assignment you just submitted on Monday. You have questions regarding this before we move on? I see there's something in the chat. Everything. So it's a programming course. So everything, right, that you've covered, that we've covered in the course is going to be included. Yeah, but definitely the focus will be on, more recent stuff like classes. You have an assignment that is going to be out today, and it's going to be due in a week. So the last day of classes on Wednesday next week. Yeah, so we're giving you a week, and that assignment will be on the topic we're going to discuss starting today. But you can submit it on next Wednesday. Other questions? All right. Very good. Let's start. So the first thing I want to show you is we talked the last time about complexity. So before we get into a new topic or relatively new topic, I want to show you a cool, script that I've wrote to kind of motivate why complexity or analyzing the complexity of an algorithm or a function is very important. So I've written here a set of functions. Each one has a certain complexity. So the first one is a constant because that it loops 1,000 times, no matter what the input size is. It takes as an argument n, and then it just loops 1,000 times. Second one is logarithmic because each time I divide I by 2, as you know, and so on, right? So I have for each complexity class, whether it's constant, logarithmic, linear, log linear, so n log n. I have a function, yeah, quadratic, so n squared, cubic, and n cube, exponential, meaning 2 to the power of n, and factorial, which means n factorial. So each method, right, has this complexity. It should take, an order of operations that is in its name. Yeah, so if it's factorial, then it takes, factorial n operations to run. And I'm doing this throughout. What's important, not what these functions are doing. Believe me that these are their complexity orders. And what I'm trying to do is I'm going to run it for different values of n, its input, and see how much time it takes, right? To kind of tell you that really, there are certain complexity classes that are feasible, even for very small values of n, right? And some that are not feasible if n is not so large. Okay. Yes, it's going to be the last assignment, Fed. Yeah. So this assignment coming out today is going to be the last assignment. Okay. So let's run the script. Okay. So I'm going to say the following. All right. Python order of complexity. Why? I'm going to give it n as 10 first. Yeah. What is it doing? It's printing for each method how much time it took. How do I calculate the time? I just see, before the method is called, what is the current time? And then after the method is called, what is the current time? So constant takes, this time, really insignificant because it's a loop that runs 1,000 times. Logarithmic, right, takes this amount. So it's actually even less because n is 10. Log 10 is definitely less than 1,000, right? And then the linear took this time. Anyway, all of them finished. For n is equal to 10, it's not a big deal, right? You see that the factorial took, relatively more time, but in general, all of them finished. Let's run it again, increasing the input size a bit. So 100, right? So I have 100 elements. yeah, or n is equal to 100. What do you notice now? Constant finished, logarithmic finished relatively fast. Everything until cubic finished very fast, right? And now we're waiting for the exponential and the factorial. Yeah, they might take some time. They might take even hours, even for such a small input as n equal to 100. Yeah. So what I'm trying to tell you is the following, right? If you write up an algorithm and you analyze its complexity and its factorial or exponential, then there is no point in using it. Yeah, because even for such a small input size like 100, it will take a lot of time to execute. So it's not finishing. It hasn't finished yet. Yeah, I'm gonna stop it.
Professor.
Yeah.
Professor.
Yes, go ahead.
You meant it could take hours to get computed?
Yeah, it could take hours to finish, right, the function, right? So for this method, right, the exponential, which just basically loops 2 to the power of 100, might take hours to finish, right? Even on my laptop, which is relatively fast. Why? Because exponential is very infeasible. Yeah, exponential 2 to the power 100 is a really large number. 100 factorial is even a larger number, right? So if I loop 100 factorial, or if I loop, 2 to the power of 100, that's going to take a lot of time, yeah, because I'm waiting for it to finish the loop before I'm done with this method. Is that clear? Okay, so let's try it again. I'm going to try to increase the input size a little bit. So not 100, but 1000. And let's see what happens. Now, it finished the constant, the logarithmic, the linear, the log linear, which is n log n, quadratic, and now it's stuck at the cubic. So even for just, a relatively small number, right, 1000, it's not too big. 1000 to the power of 3 is, again, a lot of loops. Yeah, it's going to do, like basically 1 and then 9 zeros, right, loops. And that's a lot of things, right? It's executing, it's taking time. So even cubic is not recommended. So if you have an algorithm that is cubic, it's not recommended for if your input size is too large. It's going to take a lot of time. Yeah. So imagine that you're searching through a list and it has 1000 elements, or you're searching in a library, for a book, and the book has 1000, the library has 1000 books, right, in its database. If you have a cubic algorithm for searching, then it's useless. Yeah? We're going to have to wait, a long time to be able to get a response or an answer to my query. Okay, and of course, the more I increase, if I increase this to 1 million, let's say, the quadratic is gonna start taking more time. Yeah, so now the linear finished, log linear is finished, and it took relatively more time than before, and now we're waiting for quadratic. Yeah? So these complexities matter, yeah, and it matters based on your input size. That's really the take home from this exercise. Okay, so now basically even quadratic is not finishing with 1 million elements, or just doing 1 million loops to the power of 2 is going to take a lot of time. Okay. Questions about this? Okay. Now let's talk about, not exactly something new. We've seen this before, and it builds on complexity to an extent. We're going to talk about, searching and sorting, particularly a list. Okay. So assume the following. Assume we've seen this before, but I'm going to repeat it here for the sake of completeness before I get into sorting. So what is searching a list? It's really, you're given a list and you want to find the index of an element inside this list if it's found. So I want to say, the element is the third element or the fifth element, or, the element number 100. And I want to return -1 if it's not found. Of course, there are, in Python, there is, a function to return, whether an element is in a list or not, but we want to write this from scratch. We want to write our code from scratch. So your method should be taking a list as an input, an element, an integer, right, in our example, x, and it should, try to find out whether it is in the list or not, and return its position in the list if it's there. Okay, we've seen this before. Here's the most simple method or way to do this, is to just do a linear search. So go over the list element by element, check The first element is my X. So L is the list that I want to search in, and X is the element I'm looking for. So I'm going to check, is the current element in the list is equal to X? If yes, I return its index, so its position in the list, the third, the fifth element, and so on. And I keep doing the search or looping until I reach the end of the list. If I reach the end of the list and this if condition was never satisfied, I'm gonna return -1. If this condition is ever satisfied at any point of time, the function stops, right? So because I'm returning the index, so the function would return the index to the caller of the event, right? That's really linear search. We've seen it before. Any questions about the pseudocode or the code itself before we get into complexity? You will agree that this function would work. What it does, it just looks for this element X inside that. If a function has a list output that has 2 to the power n elements, such as that's it. So remember, right? When we're talking about this Rawat, so Rawat is asking a question, right? Again, I prefer if you ask the questions to everyone so that everybody can follow Rawat, right? So when I say 2 to the power of n, the complexity of the function is 2 to the power of n, right? And if it's an iterative algorithm, it means that the loop runs 2 to the power of n times, where n is the input, yeah? So it could be the length of the list, something like this. It doesn't mean, right? If the elements have 2 to the power of I, so they're not, they 1, 2, 4, 8, right? Are you doing something with this list? So how long is this list, right? Assuming that this is a list, yeah? So how long is this list, and whether you loop until you finish the list. That's what tells you the complexity. It's not that the elements are 2 to the power of I, it's that I have to run number of iterations equal 2 to the power of n. That's really what made the complexity of this function. So this function that I have here, it's just basically running, right, from 2 to the power of n until 0. So to the power of n, to the power of n minus 1, to the power of n minus 2, until 0. That's 2 to the power of n times. I understand what you mean, Rawat. What I'm saying is it depends, right? How long is the list? Yeah, assuming that you will go through all the elements of the list. Doesn't matter what the elements are. They could be A, B, C, D, could be 1, 2, 4, 8, 16. The question is, how long is this list? You have to see, and whether you're looping over the whole list or not, right? The question is a little bit vague. Okay, we can discuss it after class if you want. Okay, getting back to linear search. Any questions about the pseudocode? Right. I need you to do something for me, all of you. I need you to tell me what is the complexity of this function. Anybody knows what is this big O of? The pseudocode is shown here. Any thoughts? What do I do? How do I figure this out? You have this in the exam, right? So maybe it's on Friday. So you might want to, basically not searching, but really complexity. It's big O, as you guys say, big O of length of L. Right? There is a for loop for length of L, as Jad and Khalid and Michael are saying. So it's big O of length of L. Excellent, excellent. I see all of you now are following. It's big O of length of L. Exactly. Why? Because I have a loop that runs from 0 to length of L minus 1. That's length of L times. It's big O of length of L. So it's a linear algorithm, and hence the name linear search. Okay. We can do better than this, and we've seen this before, but I'm going to repeat it again.
Professor?
Yes.
Can you go back just to the other? Yes. For example, if you have 4 index in range 0 or 1 len L, do we say so the type complexity is O len L minus 1?
No, again, right? Remember that, right? We ignored the constants. Yeah. So length of L minus 1 is big O of length of L. It's a bound. Yeah. So really, it doesn't matter if it's big O. I'm gonna write it in the chat. Right. Let me see.
Okay.
So when you say big O, you can big O of n. That means, right? Could be something like this. Could be 2n minus 1, or it could be n plus 3. Why is it doing n plus 3? All of this is big O of n, right? Again, we ignore the constants, the constant multipliers, the addition or the subtraction. It doesn't matter. It's a big O of n, meaning order of n. Right? It's about. Does that answer your question, John? Okay, good. Now let's go back to another algorithm for doing search. This is binary search. We've seen it before. You guys have seen it before. You've done an exercise on it in one of the assignments, but it was an interact. So it's not exactly, giving an input list and an element, and you're trying to find where this element lies in this. So the idea of the binary search is the first thing we have to make, a point of, or we have to, make sure of, is that the list has to be sorted in order for you to do binary search. And the idea of binary search is that you're saying, okay, I'm going to go to the middle element in the list and check whether this element is the element I'm looking for. Okay, so we really start with the middle. It's a wild guess. Yeah, start in the middle of the list and say, okay, is this element the element I'm looking for? And if it's not, I have to see which half of the list I need to look into. So it depends on how big the element in the middle is compared to X. So let's say I have the following. I have the list is, like this: 1, 3, 5, 7, 9, 11. So important thing is that it's sorted, and I'm looking for the element 3. Right. So this is the thing I'm looking for inside this list. Okay. So I'm going to start in the middle. Let's say the middle is 7. 7, is it the same as 3? No. Then which half of the list should I look at? The 1, 3, 5 or the 9, 11? And how do I decide on this? Anybody knows? Since the list is sorted, I can discard this completely. Right? Why? Because I know that, right, 3 is less than 7, so it has to lie before 7. Yeah, that's really the intuition. So I have to look at this half only, and then I'm going to go to the middle of this, sublist now, and just check, is 3 equal to 3? Yes, I'm done searching this list into, comparison. Yeah, that's really the idea. Okay, and so on, right? No matter what the element is, all I have to say is go to the middle, check whether the element I'm looking for is the middle element. If it's not, decide whether to search in the upper half or the lower half based on, comparison between the middle element and the element X you're looking for. So here's the pseudocode. Have 3 variables, low, right, which start with the beginning of the list, because initially I have the whole list. So I'm going to start with 0, and high is the last element in the list, so that's high, and that's low. Okay. And I have X, right? That's the input. As long as, right, my L is less than or equal to high, so as long as I haven't finished searching the list, that's really what the condition is doing here. Calculate the middle element, and I'm doing integer division because low plus high, depending on the number of elements in the list or a subsequent sublists, right, it might be even or odd. Right? So I want to make sure that I get an integer right, because that's an index. Okay, so I'm going to do integer division. That would give me, roughly the middle element in the list. Okay, so that's the position of the middle element in the list. I'm checking, is this, middle element in the list is equal to X. If yes, return this mid, because I want the position. I want to say it's the 5th element or the 100th element. Otherwise, I check which half should I search for. Yeah, so in the first part here, I'm saying if X is greater than the middle element, which, not the case in our example, but if it was, I have to say, move the low to here. So now I'm looking at this sublist only, right, from low to high, because every time I'm looking from low to high. Yeah, and if it was the opposite, so if, my element was less than the middle element, I'm gonna update the high. So I'm gonna put high here, and I'm going to look between low and high. Right, so I update the low in case X is greater than. Sorry, if I update the high if X was less than of min. All right, and then I keep looping until I either find the element eventually or I finish, right, the loop, which basically when low becomes greater than high, so low crosses the high, that means you have finished looking at the list. You never found the element, I should return minus. That's really binary search. You've done something very similar. You didn't need to memorize this code, just need to understand the intuition. Yeah? If you understand how it works, you should be able to write it very easily. And there's zillions of implementations of binary search out there. There's also a recursive version of it that I encourage you to look at. Questions about it? Questions? Yeah, as I said, we've seen this before. Type. Let's see what it's complex. Can anybody tell me what the complexity of this algorithm is? Any thoughts? How many, I have a loop here, a while loop. I need to count how many times it occurs. Freddy's saying it's log n. Why is it log n, Freddy? Can you tell us? You can write in the chat if you want. Yes, Rawad is also saying log n. Okay. Length of L log n. Okay, we'll look at that one in a bit, right? Okay, but so Fadi, can you explain to us why you think it's log n, or Rawat, one of you? Okay, yeah, right. So Fadi and is saying right because of the division, and Khalid is saying, we start with the whole list, right? The first time. So the first time, right, we had these elements, right? Unlike linear search, where linear search, would go at them element by element and check from the beginning to the end. Binary search does the following, right? Starts with the whole list, then only look at 1/2, and then quarter, and then 1/8, and so on until I finish the list. The worst case, right? I will finish the list without finding the element. So in the worst case, right, I'm dividing by half each time, and we know this pattern is log or log length of L, right? Because my input is L, so log length of L. Okay, now Sergi, why do you think it's length of L times log n? First of all, there's no n, right? So do you mean that it's log length of L? That's what you mean? Or you mean that it's length of L times log n, whatever n is? Can you explain your answer, Sergi? What do you mean by length of L log n? Okay, then I'll assume that you mean just log length of L where n is, okay, where n is length of L, right? So I always have to express it in terms of the input, okay? Okay, so the complexity of the above function, right, is, as we said, log length. Okay. Okay. Let's run these algorithms just for the sake of completion, and then we'll do one more algorithm, and that's it. So I'm gonna show you, I think, binary search. Yeah. Let's just run it to just make sure that it's working correctly. Okay. So here is the input. It's 1, 2, 4, 6, 7, 10, and I'm looking for 11. It prints, -1 because the element is not there. Let's search for an element that is there. So 7, for instance. Gonna run it again, and it tells me 4. Is the index correct? 0, 1, 2, 3, 4. Okay. So basically, right, it's working correct. Of course, we have to try it. I mean, if you want to really exhaustively test it, you have to try it on, multiple lists and multiple inputs, but you can believe in that it's correct. What about this? I'm going to change something in the code. what would it answer in this case? So I changed the input, right? So I give it the list 1, 2, 4, 3, 6, 7, 8, and I'm looking for 7. If I run it, what it is going to give me? Can anybody tell me? What do you think? What's the position of 7 in this list? 0, 1, 2, 3, 4, 5. So it should give me 5. You all agree it's going to output 5 if this code is correct? Or anybody has an issue with that? The list is not sorted, right? It's not going to give me an error. It's going to just give me random value, right? Because it assumes that the list is sorted. Of course, it's not sorted, so the algorithm is wrong, right? The algorithm would not work correctly. It's going to give me some value, right? It might give me -1. It might give me, right, like a random value. But the problem is this list is not sorted. Yeah. So really, we should not apply this binary search on a list that is not sorted. Yeah. So it'll give me maybe the correct answer by luck. 1, 2, 3, 4, 5. I can add, here maybe 0. Let's see what happens. Or maybe 0 here. Yeah. It's somehow, working, but it shouldn't work. Yeah. 7 here. Yeah, so it gave me, for instance, -1 for this list, even though 7 is here. Why? Because this algorithm assumes that the list is sorted. It will only work correctly if the list is sorted. So always use binary search when the list is sorted. Which brings me to the next topic, which is sorting. Again, right, you have in Python, like built-in functions to sort, right? So really we can do l.sort or sorted of l. What we want to teach, it's a very important topic. Sorting, right, means what? Means putting elements in an order, increasing order or decreasing order. Yeah, it's a very important topic in computer science. We always like to, discuss. Okay, so many applications require sorted data, presenting a list of books ordered alphabetically, presenting a list of students ordered by the grades, something that we heavily use in all applications. Yeah, you always want to represent things in sorted order because humans like, sorting, like to see things in some order rather than a random order. Sorting can speed up searching. Why? Why sorting can speed up searching? Where did this come from? I'm claiming that sorting can speed up searching. What do I mean by this? Any thoughts? We can use, as Michael is saying, yes, you can use binary search, which is faster. Yeah? As we will see, it's not worth it to sort a list and do one binary search. But if you know that you have a list that you're going to be always searching in it, for instance, let's say it's a list of students and I'm always going to list, search student by name. I might want to sort the list first by name and then do multiple searches. Yeah? So if you have one search, right, it might be more efficient to just do linear search rather than doing binary sorting and then doing binary search. But if you have multiple, you know that you're going to search multiple times, it's better to use, sort and then do binary search. There's so many different algorithms that have been invented for sorting, and there's so many that are coming up every day. Yeah, it's really an amazing problem that so many solutions are there for it, and people tend to still work on. You always get asked about this in job interviews. So I know maybe this is early for most of you, but if you apply for Google for an internship or a job or something like this, usually the first filtering stage, which is a telephone interview, they're going to ask you about sorting. Because this is a fundamental problem in computer science, and if you are able to answer the questions, particularly regarding complexity and sorting, or how do I sort a list, like a pseudocode algorithm for sorting a list, they know that the basics at least. Yeah, so this is really something I've experienced it in almost all technical exams that I've taken. Yeah? I remember in Google, when I did an interview for an internship, first thing they asked me about was, sorting and complexity of sorting, and etc. Yeah? So it's really something that is important. Okay, so let's see one particular example of sorting. Yeah, so one algorithm for sorting. Again, there's zillions of them. We're going to look at 3 different examples here in this course, and that would be it for the material or the content of the course. But in general, there's zillions of them, and some have, work better in certain cases and so on, right, which you will get exposed to later on. So selection sort, what is this? From the name, the idea is the following. I have a list, right, of elements that are not sorted. So something like this, let's say 5, and then 2, then 1, then 4, then 7, and then 6, and then let's say 8. Right. So this list is obviously not sorted. I want to sort it ascending. Yeah, we'll assume all that I'm sorting things ascendingly. Can of course reverse this. Okay. So selection sort starts by saying, okay, I'm gonna pick the minimum element out of this list and put it as the first position. So what is the minimum of this list? If I look at it, it's 1. So I'm gonna put 1 at the first element. And then I'm going to, look at all the other elements and pick the minimum out of them and put it next. 2 is the next element, and so on, right? Out of all the elements left, so I've done this, I've done this. Out of all the elements left, 4 is the minimum, so I'm gonna pick it next. Out of all of these guys, what's the minimum? It's 5, so I'm gonna take it next. Then 6. Then out of 7 and 8, the minimum is 7. And then finally, I have 8. So that's really a very simple algorithm to do sorting, right? And it's called selection sort because I'm selecting the minimum. There's various ways of writing the code for this. We'll look at one example. But here is a video first of, how it works, right? So this is from MIT. They did a simulation of this. Let me see if I can share this while sharing the screen. Give me a second. Yeah, here it is.
All right, so now we're going to do selection sort. The idea here is at each step, we're going to select the shortest person and put them next in line of the sorted group. So we'll bring the leftmost person forward, and we will compare her to everybody else. So one at a time, step forward. You're still the winner. You go back. Please step forward. Oh, you're definitely the winner. Next. Still the winner. Next. Ah, a new winner. All right. So you can take her place. Now we'll compare. Same old winner. Same winner. No change. It's getting kind of boring. Don't fall. Same winner. Please. Oh, close, but I think you're still shorter. All right, next. No change, which means you are the first in line. Congratulations. All right, now you step forward and we'll compare you. You are the winner. Take your place in line. Next. It's you. And once again, we have a lovely group of students sorted in height order.
Okay. So just a simulation of this, right? I'll show you another example with numbers because maybe this would be easier to visualize. So I have this list, right, which has 3, 2, 4, 1, 5. It's obviously not sorted. Here's how the algorithm works, right? I start comparing 3 and 2. Since 2 is smaller than 3, I'm going to swap them. So I do swapping, then 2 becomes the first element. Compare 2 and 4. I'm trying to pick, that minimum element and put it in position of 2. Yeah. So 2 and 4, 2 is still smaller, so I move to the next element. Oh, 1 is less than 2, swap. And then 1 and 5, 1 is smaller, so it stays in this place. So after this round, I have 1, the minimum element, in the first position. I'm going to repeat the same procedure for the rest of the elements. So 3 and 4, 3 is smaller, so I don't do swap. And then I have 3 and 2. 3 is greater than 2, so I do a swap. And then 2 and 5, 2 is smaller, so I don't do a swap. After this round, I have 2 positions, the second smallest element. I'm going to repeat this starting from 4. So 4 and 3, swap. 3 and 5 stay the same. And now I have 4 and 5. Everything stayed the same, and I'm done sorting. That's really one of the most simple algorithms for sorting. Not the best, but it's one of the most simple ones. Here's the pseudocode, right? It's as simple as this. 4 lines or 5 lines, 4 lines of code plus the definition of the function. So I'm looping, over the list. So I'm doing, loop over every element in the list, and inside, try to pick the minimum element and put it in the first position. So I start with I, equal to 0, of course, right? And then J is start from the second element and compare it, right, with the current element. So, check if the first element here, L of 0, right, is it greater than L of 1, right? That's the first iteration of these two loops. L of 0, is it greater than L of 1? If yes, then swap them because I want, right, the smaller element to be first. Okay, so I'm going to swap. If not, I'll move to the next element, right, to L of 2. Compare L of 2 to L of 0. If it's L of 0 is greater, I'm going to swap them. Otherwise, I'll skip and move to the next element. So after I finish a whole, one whole round of this, loop, I would have put the smallest element in position 0. Then I increment I by 1, so I becomes 1. So now I'm looking at the second element in the current list, and I compare to all other elements inside the list. So start from 2 here all the way till the end. Again, compare so that I push, the element, the current smallest element to the second position, and so on. Yeah. Again, no need to memorize this code. There's different variations of it. For instance, there is a variation which actually, looks for the minimum element and then swaps it with the current element, right? But that does this as well. Doesn't matter. What I want you to focus on is, again, understanding the intuition behind the algorithm. Yeah, so how does it work? So you need to know what is the selection sort. How does it work? Yeah, what is its strategy or pseudocode? And what is its complexity? So questions about it, right, first. Okay, let's run it and then I'll go back to the complexity. Selection sort, here it is. Right, here's the code, exactly as in the slide. And here are the same elements as in the slide. Okay, let's run it. The code selection. .py. And here's what it does, right? It sorts the list in ascending order, right? You can give it any list, it will automatically sort it. Yeah, you can verify this. I'll put all of these scripts, of course, on Moodle so you can verify. Yeah, try to write them yourself. Okay, complexity. Can anybody tell me what is the complexity of this function, of this method? Okay, Khaled, that was fast, right? So length of L squared. Length of that judge saying length of L squared, okay. Any other thoughts? Anybody agree, disagree with them? Can you explain to me why is it length of L squared? Mohammed is saying length of L squared. Okay, can anybody explain to me why is it length of L squared? I have nested loops, correct? Nested loops means I need to do some multiplication. Yes, so 2 loops or nested loops, so I need to do multiplication. I know that. The first one, how many times does it run? Length of L, right? It's in the range of length of L. That means I'm looping over the whole list. And the second one starts with I plus 1, right? So the first time it will run, length of L minus 1. The second time it's going to run length of L minus 2, and so on, right? But we're doing worst case, right? So length of L minus 1, right? So the worst case is that I'm going to run, length of L minus 1, then length of L minus 2. So what is the maximum of all of this is length of L minus 1. If I do this in order, that's length of L squared, right? Again, why? Because I'm doing a bound and I'm doing worst case scenario. We ignore the constants, yes, sir. Yeah, so we always ignore the constants, it doesn't matter. Why? Because I'm doing this big O. What does big O mean? It means order of. It means really it's a constant times length of L squared plus or minus a constant. That's really what it means, O. Yeah, big O. Okay? Questions? Okay. So here is one important note. This algorithm is its complexity is log n squared, assuming that n squared, assuming that the length of the list is n. So what is the complexity of sorting a list and then using binary search? Who can tell me? If I use this method to search a list, so I decided I have a list that is unsorted. So I decided I'm going to do selection sort on the list first, so I can use binary search and then do binary search. What is the complexity of the whole program? So first selection sort and then calling binary search, which we just did before. Right. So my program is going to do the following: first call selection sort to sort the list, and then do binary search to search for element X in the list. Okay. So Fadi is saying it's big O of n squared. That's correct. Why is it big O of n squared? Because, right, log n is much less than n squared. That's Rawad is saying. It's really exactly right what Khalid is saying here, right? It's saying, right, it's log length of L squared plus log length of L. Well, we take only the n squared because it dominates, right? It's much bigger than, log n. Exactly. So we just take, so it's big O of n squared time. So if I use selection sort and then binary search, I will do big O of n squared. My program is going to be, take n squared operations, order of n squared operation. Right. If I just did linear search on the list without any, sorting or binary search, what is the complexity? So instead of doing this, I'm going to do just linear search. Yeah, it doesn't matter. Linear search works for even if the list is unsorted. What would the complexity be? It's going to be big O of n, where n is the length of the list. So which one would you choose? Which strategy would you choose? Should I do search, sorting and then binary search, or do linear search? Which approach? Yes, log length of L is smaller, right? So small that we can neglect it compared to n squared, Jet. Now, here is the question, right? Would I use this program or should I use this program? Which one is faster? That big O of course, right? So, however, if I'm doing multiple of these, so if I'm doing, I'm going to search, let's say order of n, right? Or, or something like this, the elements where I know that I'm going to search a lot, then it might be cheaper to, do this instead of doing, to use selection sort instead of, to sort first the list and do binary search instead of using linear search. Okay, that's really that trick, right? If you're just doing one or few, searches and the list is not sorted, it's better to use linear search in general. We'll see later on an algorithm, right, that has a better complexity than this, right, that n squared. So this most common, sorting algorithms are big O of n squared, but we'll see one that is actually faster than this. There's few of them that are faster, but we'll only look at one. All right, we can stop here. On Friday, we'll mostly, discuss questions if you have, and maybe, look at one more sorting algorithm depending on the time.